Look up. On a clear night, far from the glow of cities, the sky becomes a tapestry of light. Stars are scattered like cooling embers, and the pale ribbon of the Milky Way arches silently overhead. It all feels so permanent, so calm. But that sense of peace is an illusion born of distance. Across the cosmos, beyond the gentle constellations we learn as children, there exist places where the very ideas of space, time, and matter warp into something closer to nightmare. They are not merely hostile, they are realms where the universe strips away every comfort we cling to, revealing a reality that is vast, indifferent, and utterly terrifying. So, what are the most terrifying places in the universe, and what do they reveal about the nature of reality itself? These are the corners that do not just sit silently in the dark. They actively devour light, twist gravity into a weapon, erase entire galaxies from our sight, or stretch the fabric of existence until it can stretch no more. From bottomless voids that span hundreds of millions of light years to the invisible gravitational currents dragging entire clusters toward an unseen fate, to the dying stars that become the most magnetic objects in existence, the cosmos hides its most horrifying features behind a curtain of tranquil beauty. This is a journey into the darkness between the stars and beyond them, a journey into the most terrifying places in the universe. We have to start with emptiness, but not the familiar emptiness of a vacuum chamber or the space between planets. We have to start with an emptiness on a scale that shatters the imagination. To understand it, we first need to erase a common misconception. A cosmic void is not a region of pure nothing. It sounds like a paradox, but the universe simply does not do absolute zero. Even its most deserted districts still contain a whisper of matter. A thin, nearly invisible haze of hydrogen atoms drifts through them. A faint bath of primordial light from the Big Bang still washes through their spaces. There are scattered particles of dark matter, and the occasional lonely galaxy that wandered in from the filamentary highways of the cosmic web. The difference is density. In a typical volume of space, you might find clusters of thousands of galaxies, blazing with starlight and structured by gravity into a sprawling network of threads and nodes. In a void, that density collapses. The gaps between galaxies become so immense that you could traverse 100 million light years and never brush against a single major galaxy. The cosmic web, the largest known structure in nature, looks something like a foam of soap bubbles. The walls of those bubbles are made of galaxies and dark matter, while the interiors are the voids. Our Milky Way sits on the edge of one such bubble, a modest underdensity called the local void. But there exist voids that make our local empty patch feel crowded. One of them is the Boötes void, lying roughly 700 million light-years away in the direction of the constellation Boötes. This is a cavity that astronomers sometimes refer to simply as the Great Nothing. It was discovered in the early 1980s during extensive redshift surveys. Researchers were painstakingly mapping the three-dimensional positions of thousands of galaxies, and as they filled in the map, a hole began to appear. A hole nearly 330 million light-years across. To put that in perspective, the distance between our Milky Way and our nearest large spiral neighbor, Andromeda, is about 2.5 million light-years. You could stack more than 130 copies of that intergalactic gulf end to end, and they would still fit comfortably inside the Boötes void. Based on the average density of the observable universe, a sphere of that size should contain somewhere around 10,000 galaxies. Instead, as of today, we have found fewer than 60 small, faint specimens drifting inside it. That is not an exaggeration. It is a statistical scream of absence. If you could magically transport yourself to the center of the Boötes void and look out with naked eyes, what would you see? Not a star field, not a single point of light would be visible unless you happened to catch the faint gleam of one of those rare dwarf galaxies, which would appear as a fuzzy, barely there smudge, no brighter than a piece of tracing paper held against a dark wall. For the most part, your entire field of view would be a seamless, velvet blackness in every direction. No Milky Way sweeping overhead, no familiar constellations. The nearest substantial galaxy might be so far away that its light would take hundreds of millions of years to reach you, meaning the image you would eventually see would be a ghost from a time when dinosaurs still roamed the Earth. The cosmic microwave background, the faint afterglow of creation that fills all space, would even look slightly dimmer, sapped of energy as photons climb out of the shallow gravitational well of this immense underdensity. You wouldn't just feel alone. You would be alone in a way evolution never prepared a mind to comprehend. But how did such a monster come to be? The leading theory is that the Boötes void is not a single clean cavity, but the product of multiple smaller voids merging. In the early universe, tiny quantum fluctuations in density set the stage. Slightly denser regions pulled in matter through gravity, growing into the filaments and clusters we see today. Meanwhile, slightly less dense regions lost matter to their surroundings, expanding into larger and larger bubbles of emptiness. Over billions of years, dark energy accelerated the expansion, and these bubbles coalesced into supervoids. The Boötes void might be the gaping scar left behind when several such regions combined, matter streaming out along the surrounding walls like water draining from a basin. There are even speculative, far-flung ideas that such a region could be the footprint of a collision between our universe and another in the distant past, though no evidence supports that yet. The raw physical explanation, however eerie, is more than enough. And this is where the terror of voids takes a philosophical turn. For a long time, the emptiness of these regions was seen as a cosmic desert, sterile and irrelevant to life. But a growing number of researchers are asking a strange question. Could cosmic voids actually be the best places for intelligent life to emerge? The reasoning is counterintuitive but compelling. The most common killers of complex biospheres in the universe are not internal disasters, but cosmic ones. Nearby supernova explosions that strip away planetary atmospheres, gamma-ray bursts that flood a world with lethal radiation, gravitational perturbations that hurl comets inward. In the dense, star-packed regions of galaxy clusters, these catastrophes are frighteningly frequent. A world in the middle of a rich cluster might be hit by a sterilizing event every few 100 million years, just when complex life starts getting interesting. But in the quiet, isolated dark of a void, the pace of violence slows to a crawl. Galaxies are so few and far between that the chance of a lethal burst sweeping through and hitting a specific planet becomes astronomically low. Life in a void might have billions of years of uninterrupted peace, a tranquil nursery where evolution can unfold without cosmic reset buttons being slammed repeatedly. The trade-off is isolation. In a void, civilizations would be stranded. They could look into a night sky that was almost entirely empty, and any neighbors they might develop radio technology to reach would be separated by such incomprehensible distances that communication would be a message sent into a silent millennium. They might never realize the universe is teeming with galaxies at all, because from deep inside a super void, only the brightest objects on the far walls would ever be detectable. The Boötes void, for all its terrifying emptiness, might be a cradle, but a cradle floating alone on an infinite black sea. And we, sitting at the edge of a modest void ourselves, are perhaps in a middle ground, close enough to see the rich cosmic web, but far enough from deadly cluster cores to enjoy a somewhat peaceful galactic address. The Boötes void, then, is not just a hole. It is a window into the deep logic of cosmic architecture. If the Boötes void is a vast valley of absence, there is another region that is even more disturbing, because it does not just lack galaxies. It seems to have stolen energy from the oldest light in the universe. It is called the Eridanus supervoid, and it shows up as a cold wound on the afterimage of creation. The cosmic microwave background, or CMB, is a nearly uniform bath of microwave radiation left over from about 380,000 years after the Big Bang. It varies in temperature by only tiny fractions of a degree, but those variations map the seeds of all cosmic structure. In 2004, data from the WMAP satellite and later the Planck Observatory revealed a spot on that map that was significantly colder than anywhere else. They called it the CMB cold spot, a region spanning about 1 billion light-years in projected size. When astronomers looked at the normal matter in that direction, they found an enormous supervoid in the constellation Eridanus, a place where galaxies thin out drastically across 1 billion light-years of space. The alignment was too strong to be coincidence. The cold spot lined up with the Eridanus supervoid. The physics behind the coldness is a phenomenon known as the integrated Sachs-Wolf effect. As CMB photons travel through the expanding universe, they pass through gravitational wells. In a dense supercluster, a photon gains a tiny bit of energy falling in, but loses it climbing out. If dark energy is stretching space while the photon is inside, the balance shifts slightly. In a supervoid, the opposite happens. The photon loses more energy climbing out of the void's shallower gravitational well than it gained falling in, because the well itself has been stretched and shallowed over cosmic time by the accelerated expansion. The result is that light emerging from a supervoid is just a fraction colder, like a fossilized chill. It is as if the void itself left a frostbite mark on the oldest light we can see. But the size of the Eridanus supervoid is what rattles physicists. It is so large that it strains the standard model of cosmology. In simulations, supervoids of this magnitude should be vanishingly rare. You might expect 1 or 2 across the entire observable universe, but the fact that we see this one prominent cold spot raises uncomfortable questions. Some alternative theories have proposed that the cold spot could be the imprint of a collision between our universe and another bubble universe in a larger multiverse, a bruise on the skin of our reality. While the void explanation remains the most widely accepted, its sheer scale continues to make it an object of intense cosmic unease. It is a place where the universe's first light seems to have been damaged, a hollow cold enough to be felt across 14 billion years. Now, if voids are the great empty hollows of the cosmos, their counterparts are the dense knots of gravity that pull everything else toward them. And the most famous of these is an invisible behemoth that has our entire galaxy trapped in its pull. We call it the Great Attractor. The attractor is not a single object. It is not a giant black hole or a monster star. It is a region of space, a gravitational basin roughly 200 million light-years away in the direction of the constellations Norma and Centaurus. Its influence, however, is anything but local. The Milky Way, Andromeda, and the entire local group of galaxies are currently moving toward it at about 600 kilometers per second. That is more than 2 million kilometers per hour. This is not a drift through space. It is a coherent plunge along a cosmic river that encompasses the motions of tens of thousands of galaxies. The attractor's mass is estimated to be on the order of millions of billions of solar masses, but until recently, we could not even confirm what was there. The trouble is its location. It sits squarely behind the zone of avoidance, the dense disk of our own Milky Way that blots out optical light from that patch of sky. Trying to see the Great Attractor through visible telescopes is like trying to read a book through a thick, glowing fog. Only X-ray and radio surveys have slowly pierced the veil, revealing the massive Norma cluster at its heart, a collection of hundreds of galaxies embedded in a cloud of searing hot gas. But the Norma cluster alone cannot account for the motion. The pull extends far beyond it, suggesting that the Great Attractor is just the local basement of an even larger structure, the Laniakea supercluster, which itself is being tugged toward the even more massive Shapley supercluster beyond. This is where the relationship between voids and attractors becomes a story of cosmic push and pull. The cosmic web is not a static sculpture, it is a dynamic flow. Galaxies are birthed in filaments, but the vast empty voids act as pressure sources, their lack of mass creating a kind of gravitational repulsion relative to the dense nodes. Matter naturally drains out of voids, sliding along the filaments and converging on the supercluster nodes at the intersections. The Great Attractor sits at one such intersection, and the immense voids that surround it, including our own local void to one side and a mysterious deep void on the other, help funnel the flow. Our local group is not just being pulled by the attractor, it is being pushed as well. Astronomers have recently confirmed the existence of what they call the dipole repeller, a massive underdensity on the opposite side of us from the Great Attractor. The repeller is essentially a giant void, a region of space so profoundly empty that it generates an effective outward push on the galaxies near it because there is so little mass to hold them back. We are caught between a pull and a push, a gravitational tug-of-war orchestrated by the combined architecture of superclusters and supervoids. Every galaxy streaming toward the Great Attractor is a testimony to the voids that expelled it. The Boötes void, the Eridanus supervoid, the dipole repeller, all the great empty chambers of the cosmos are not passive absences. They are active sculptors, and their relationship with the attractors is the engine of large-scale structure. If you could watch from a godlike perspective, you would see entire civilizations of galaxies pouring out of vast, empty bubbles, sliding along glowing tendrils of dark matter and pooling into a gravitational sinkhole that is the great attractor. Our own sun, our planet, our very bodies are part of this falling stream, a motion that will never stop, only change direction as the local nodes merge and deeper attractors reveal themselves in the distant dark. The journey will take hundreds of millions of years, and by the time the Milky Way approaches the attractor's heart, the Earth and Sun will be long dead. But the silence of that motion, the inevitability of it, is deeply terrifying. We are on a train with no brakes, heading toward a destination we cannot directly see, driven in part by the repulsive emptiness behind us. From the gravitational quiet of supervoids to the unseen currents they create, we now turn from the largest scales to some of the smallest objects that generate the most violent destructive power. Because if voids are the most desolate places, then magnetars are the universe's most furious iron fists, crushed stellar remnants that pack an entire sun's rage into the volume of a city. When a massive star, say 20 times the mass of the sun, exhausts its fuel, its core collapses catastrophically. The outer layers blow apart in a supernova, while the inner core crunches into something incredibly dense. If the core's mass is just below the threshold for forming a black hole, it becomes a neutron star, a sphere only about 20 kilometers wide, but so dense that a teaspoon of its material would outweigh Mount Everest. Neutron stars are already extreme, but roughly 1 in 10 is born spinning fast enough and with magnetic fields twisted into knots so intense that it becomes a magnetar. The numbers are barely believable. A refrigerator magnet has a strength of about 0.01 Tesla. Earth's magnetic field, the one that gently turns compass needles, is about 0.00005 Tesla. A medical MRI machine can reach a few Tesla. A magnetar's surface field can exceed 100 trillion Tesla. That is not a typo. It is a magnetic field so powerful that if you somehow found yourself within 1,000 kilometers of one, the magnetic force would distort the very electron clouds that hold your atoms together. Molecules would stretch into thin, needle-like shapes. Chemistry would stop working. You would be disassembled at the atomic level without ever touching the star. But the true horror of magnetars is that their magnetic fields are unstable. The solid outer crust of the neutron star is under unimaginable stress, and occasionally it buckles. This is called a starquake. When it happens, the crust cracks, shifting by perhaps a millimeter, and the anchored magnetic field lines snap and reconnect with a violence that releases as much energy in 1/10 of a second as our sun emits in 100,000 years. The result is a flare of soft gamma rays and X-rays so brilliant that it can outshine the entire rest of the galaxy in that narrow spectrum. On December 27, 2004, a magnetar known as SGR 1806-20, located about 50,000 light-years away on the far side of the Milky Way, let off such a giant flare. It arrived at Earth like a flashbulb in the dark. It ionized our planet's upper atmosphere and partially disrupted long-range radio communications. It was so intense that it physically compressed our ionosphere from tens of thousands of light-years away. Astrophysicists calculated that if the magnetar had been only 10 light-years from Earth instead of 50,000, the flare would have delivered a fatal blow, stripping away the ozone layer, irradiating the surface, and causing a mass extinction in an instant. No warning, no defense, just a silent, invisible pulse of death. Magnetars do not live long by cosmic standards. Their insane magnetic fields drain their rotational energy over about 10,000 years, after which they settle into ordinary neutron stars. But while they are active, they are ticking time bombs scattered throughout every galaxy. There are likely tens of millions of magnetars in the Milky Way right now, most of them quiet, waiting. In the terrifying catalog of places in the universe, a magnetar's surface is not just a location, it is a weapon, a reminder that the cosmos can concentrate ferocity into the tiniest of packages. The quiet between the stars is not always quiet. Sometimes it hides a sleeping dragon. If magnetars are piercing screams in the dark, then quasars are the roaring furnaces that defined entire epochs of cosmic history. A quasar is the blazing heart of a galaxy that contains a supermassive black hole in a feeding frenzy. Nearly every large galaxy harbors a giant black hole at its center. Our own Milky Way has one about 4 million solar masses named Sagittarius A, but it is subdued, starving, radiating almost nothing. A quasar's black hole, by contrast, is glutted with falling gas, dust, and shredded stars. This material does not fall straight in. It spirals into an accretion disk, a flat, swirling carousel heated by friction and magnetic fields to temperatures of millions of degrees. The disk glows brighter than the combined starlight of the host galaxy's hundreds of billions of suns. Jets of charged particles erupt from the poles at nearly the speed of light, slicing through intergalactic space for millions of light years. If one of those jets were to aim directly at Earth, the particle beam would sterilize the planet in a cosmic instant, irradiating the atmosphere and stripping it away entirely. The most powerful known quasar is TON 618. Its central black hole weighs in at a staggering 66 billion times the mass of the Sun. That is a number that defies any human sense of scale. A single object, its event horizon stretching out a region larger than our entire solar system, is capable of swallowing entire clusters of stars without a flicker. And the energy pouring out from its accretion disk is so immense that if you could stand at a safe distance and look toward it, the light would be 1 billion times more luminous than the Sun. It would burn itself into your awareness as an almost spiritual brightness, a point of pure, silent fury holding steady in the sky. Quasars were far more common in the early universe, during an era sometimes called the Cosmic Dawn. Billions of years ago, galaxies were colliding and merging, feeding their central black holes with rivers of cold gas. The light from those ancient quasars is only now reaching us after traveling for most of the age of the universe. When we see them, we are looking directly into the past, into a time when the cosmos was younger, more violent, and ablaze with these titanic beacons. They remind us that the universe is not a place of permanent stillness. It is a dynamo of gravity and energy, able to transform the darkness itself into a blinding testament to destruction. And yet, like all things, even quasars fade. As their fuel runs out, their radiance dims, and the central black hole returns to silence, a sleeping giant at the core of a quiet galaxy, waiting perhaps for its next meal, 1 billion years from now. But while quasars shine with stolen light, the black holes at their hearts hide a deeper terror. They are not just engines of brilliance. They are places where the universe curls in on itself. At the edge of every black hole lies the most terrifying boundary in existence, the event horizon, the point of no return. A black hole begins as the collapsed core of a massive star, crushed so completely that not even light can escape its gravitational grip. The event horizon is the invisible shell that marks the limit of that grip. Cross it, and every possible path ahead leads only one way, deeper into the abyss. To an outside observer, matter falling toward a black hole seems to slow down and freeze, its light stretched into dim red nothingness. But for the falling object itself, time continues normally. It simply never returns. Imagine drifting near a supermassive black hole. From your perspective, the rest of the universe would appear to accelerate wildly. Stars would age and die, galaxies would collide and merge, eons would pass in moments while you hang at the edge of eternity. That is because black holes do not just warp space, they warp time itself. And what lies beyond the event horizon remains one of the greatest mysteries in physics. At the center, theory predicts a singularity, a point of infinite density where the known laws of nature collapse. Here, the equations of general relativity break down, and quantum physics offers no clear answers. It is as though the universe refuses to reveal what happens next. If you were to fall in, your fate would depend on the size of the black hole. In a smaller stellar mass black hole, tidal forces would tear you apart long before you reach the center, stretching you into a thin stream of atoms in a process called spaghettification. But in a supermassive black hole like the one in TON 618, you could cross the event horizon without feeling a thing, completely unaware that every direction now leads inward toward an unknowable end. In 2019, the Event Horizon Telescope gave humanity its first glimpse of this boundary, a glowing ring of hot gas circling a dark void at the heart of the galaxy M87, 55 million light-years away. It was the shadow of a black hole, not the object itself, but the fiery chaos of matter spiraling into oblivion. The image was a meditation on limits, a visual whisper that there are thresholds beyond which reality as we understand it simply ceases. The event horizon is not just a place. It is a curtain drawn across the greatest secrets of nature, a boundary where space folds, time holds, and everything that enters becomes part of a cosmic silence we may never be able to penetrate. And beyond even the gravitational grip of black holes, there is another horizon, not a boundary you could ever reach, but one that encloses everything we can ever know. It is the edge of the observable universe. For as long as humanity has looked up, we have wondered how far it all goes. The truth is, there is an edge, not of the universe itself, but of what we are able to see. The observable universe spans about 93 billion light-years across. Inside that immense bubble live every galaxy, every star, every photon that has had time to reach us since the beginning of cosmic history. But beyond that spherical horizon, there may be more, perhaps infinitely more, and yet no signal, no particle, no whisper of information from those regions will ever greet our telescopes, because the universe is not static. It is expanding, not like an explosion into pre-existing emptiness, but as space itself stretches, carrying galaxies away from one another. The farther something is from us, the faster it recedes, and at some unimaginable distance that recession speed exceeds the speed of light. When that happens, the object slips beyond our cosmic horizon. It becomes forever invisible, forever unreachable. Imagine watching the universe dissolve in slow motion. One by one, the most distant galaxies fade from view, their light stretched into longer and longer wavelengths until they slip into a radio whisper and then into nothing. What we are left with is an ever-shrinking island of visibility, a cosmic prison not of walls, but of physics itself. The light we see from the edge today is ancient, 13.8 billion years old. It is the faint afterglow of the Big Bang, the cosmic microwave background. When we observe that light, we are not seeing stars or planets. We are seeing the universe itself as a newborn, a glowing fog of particles before the first galaxies ever formed. That gentle, all-sky glow is the edge of our map. Beyond it lies a realm that no telescope, no probe, no human mind can ever reach. It is not just distance that separates us, it is time itself. The space beyond that limit is extending away faster than information can cross it, sealing it forever outside our universe's horizon, and yet we know it must exist. Galaxies, clusters, perhaps even other universes, all continuing beyond what we can see. Reality does not end at the edge of the observable universe. Only our ability to witness it does. In a sense, looking to that edge is like looking into a cosmic mirror. We are seeing not just how far we can go, but how small we really are. The horizon reminds us that even with all our technology, our understanding and our ambition, there are boundaries we cannot break. It is the universe's way of telling us this is as far as light has carried you, and beyond that lies the unknown. So, we return to where we began, not with an ending, but with a quiet reflection. The most terrifying places in the universe are not terrifying only because they threaten to destroy us. They are terrifying because they reveal our true position in the cosmos. The Boötes void and the Eridanus supervoid show us the scale of emptiness that shapes the architecture of everything. The Great Attractor reminds us that we are carried by forces far larger than ourselves, pushed and pulled by voids and superclusters in a cosmic dance we did not choose. Magnetars and quasars demonstrate that violence and energy can be compressed into forms that defy intuition, burning fiercely and then fading into silence. The event horizon teaches us that there are boundaries beyond which knowledge itself cannot pass, and the edge of the observable universe encloses the entire drama in a sphere that is both our home and our prison. These places are not science fiction. They are the real features of the universe we inhabit, as real as the ground beneath your feet. And perhaps, in acknowledging them, we find a strange comfort. The universe does not need us, and yet we are here to witness it, to trace its dark corners and quiet horrors with our small, curious minds. That act of looking, of knowing, is an act of courage. And in the end, what could be more terrifying or more beautiful than a universe that stretches beyond imagination, a horizon that recedes faster than we can chase it, and an endless expanse of existence we will never touch? The edge of the observable universe is not a wall. It is a curtain drawn across the greatest mystery of all. What lies beyond our cosmic sight? We may never know. But the stillness of that question is a gentle lullaby, inviting us to rest in the acceptance that some mysteries are not meant to be solved, only admired from a distance in the calm, dark quiet of a universe that is both terrifying and profoundly peaceful at the same time. In the cold, silent void beyond Neptune, something is stirring. Not a comet, not an asteroid. Something massive. Something that has been hiding for billions of years, leaving only ghostly fingerprints in the orbits of distant icy worlds. And for decades, astronomers thought they knew what it was. A hidden planet, born right here in our solar system, kicked out to the deep freeze by the young giants. But a new idea is creeping into the conversation, one that sounds like science fiction, that this hidden world might not belong here at all, that it could be a rogue, a wanderer from another star, captured by our sun in a rare, violent gravitational dance. Did the sun pull a rogue planet into the solar system? And if so, what does that mean for everything we thought we knew about our cosmic neighborhood? Let's start with a story you've probably heard before. In 1781, William Herschel, an English astronomer with a homemade telescope, was scanning the sky for comets. He found something that moved slowly against the fixed stars. At first, he thought it was a comet. It had a faint, fuzzy disk. But as he tracked it over weeks, its orbit became clear. It was a planet orbiting the sun far beyond Saturn. They called it Uranus. And for a while, that was that. The solar system had 7 planets, neatly arranged. But then, something odd happened. Uranus didn't obey the rules. Its orbit wobbled, just slightly, a tiny deviation from Newton's law of universal gravitation. Astronomers scratched their heads. Maybe Newton was wrong. Or maybe, just maybe, there was another planet out there pulling on Uranus with its gravity. Enter Urbain Le Verrier, a French mathematician who decided to solve the problem with pure math. He calculated where an unseen planet would have to be to cause that wobble. He sent his prediction to the Berlin Observatory. On the night of September 23, 1846, astronomer Johann Galle pointed his telescope at the exact spot Le Verrier had specified. And there it was, Neptune, right where the math said it would be. It was a triumph of celestial mechanics, and it set a precedent. When orbits misbehave, look for an unseen planet. Fast forward to the late 20th century, and we started to see another set of strange orbital patterns. But this time, they were far beyond Neptune, in a region called the Kuiper Belt. The Kuiper Belt is a vast disk of icy debris left over from the formation of the solar system, stretching from roughly 30 to 50 astronomical units, an astronomical unit being the distance from Earth to the Sun, about 150 million kilometers. It's home to Pluto, Eris, Makemake, and tens of thousands of smaller bodies. And in the early 2000s, as telescopes got better, astronomers began to notice something curious about the most distant objects in the Kuiper Belt, the ones that orbit beyond 50 AU, way out in the scattered disk. Their orbits were clustered. They all tilted in the same direction, with similar orientations, as if something was herding them. That's when Mike Brown and Konstantin Batygin, 2 astronomers at Caltech, started to pay attention. In 2016, they published a paper that set the astronomical world on fire. They argued that the clustering of these extreme Kuiper Belt objects could only be explained by a large, distant planet, roughly 5 to 10 times the mass of Earth. orbiting somewhere between 400 and 800 astronomical units from the Sun. They called it Planet 9. It was not a new idea. The concept of a Planet X beyond Neptune had been around for over a century. Percival Lowell searched for it in the early 1900s, leading to the discovery of Pluto in 1930. But Pluto was too small to explain the wobbles of Uranus and Neptune. The modern Planet 9 was different, much larger, much farther out. But hold on, there's a naming convention that often gets confused. Planet X historically refers to any hypothetical planet beyond Neptune, but it's often used interchangeably with Planet 9. However, the two are not exactly the same. Planet X was originally proposed to explain anomalies in the orbits of Uranus and Neptune, anomalies that later turned out to be observational errors. Planet 9, on the other hand, is specifically the hypothesized massive planet invoked to explain the clustering of distant Kuiper Belt objects. And it's not a rogue planet yet. It was presumed to be a native of our solar system, formed from the same disk of gas and dust that gave birth to Jupiter, Saturn, and the rest. It was thought to have been ejected inward or outward during the chaotic early days of the solar system, when the giant planets migrated and tossed smaller bodies around like cosmic billiard balls. But then, something else showed up. A different kind of anomaly, closer in. Between 80 and 200 astronomical units, astronomers noticed that the Kuiper Belt itself wasn't flat. It had a warp, a tilt of about 15 degrees relative to the plane of the planets. The outermost part of the disk was slightly bent, like a vinyl record that got warped near the edge. And this warp couldn't be explained by Planet 9. According to simulations, a planet at 500 AU would be too far away and its gravitational influence too weak to maintain that specific tilt. Something else was doing it. A team at Princeton University ran the numbers. They modeled the gravitational effect of a hidden object on that warped disk. And the best fit wasn't a mini-Neptune like Planet 9. It was a terrestrial world, a rocky planet somewhere between the mass of Mercury and Earth, orbiting at roughly 150 AU, well inside the hypothesized range for Planet 9. They called it Planet Y, a rocky world, not a gas giant. And that changed everything. Because a rocky world at 150 AU is hard to explain. The disk of gas and dust that formed the planets was densest near the Sun. Out at 150 AU, the material was too thin to coalesce into an Earth-sized planet. The solar nebula simply didn't have enough mass at that distance. So, how did Planet Y get there? Two possibilities emerge. One, it formed closer to the Sun, maybe in the inner solar system, and was kicked out by a gravitational slingshot with Jupiter or Saturn. That's the ejection scenario, a native planet exiled to the outer darkness. The other is far more exotic. It came from outside the solar system entirely. A rogue planet. A rogue planet is a planet that doesn't orbit any star. It wanders the galaxy alone, ejected from its own star system during formation, or perhaps never captured by any star at all. Estimates from gravitational microlensing surveys suggest there may be more rogue planets than stars in the Milky Way, perhaps trillions of them. They drift through the interstellar medium, dark and cold, only occasionally lighting up when they pass in front of a distant star. Most are small, rocky, and icy worlds, but some could be gas giants. And occasionally, one might stray too close to a star like our Sun. If that star's gravity is strong enough, and if the rogue comes in at the right angle and speed, it could be captured. permanently snared into an orbit around the Sun. The concept of stellar capture is not new. Interstellar objects have been observed in our solar system. Oumuamua in 2017 and Comet Borisov in 2019. Both were visitors from other star systems passing through. But capturing an object permanently is much harder. For a rogue planet to become bound to the Sun, it has to lose enough energy to fall into a stable orbit. That can happen if the rogue passes close to another planet, like Jupiter, which can steal some of its energy and fling it inward, or if the rogue interacts with the Sun's gravitational field in a way that transfers angular momentum. It's a rare event, but over billions of years, it's statistically possible. And if our Sun did capture a rogue planet, that planet would likely end up on a highly elliptical distant orbit, precisely the kind of orbit that Planet Y or Planet 9 might have. So let's imagine that scenario. A rogue planet, perhaps a rocky world the size of Earth, wandering through the interstellar void for millions or billions of years. It's cold, its atmosphere frozen to the surface, its interior still warm from radioactive decay, but not hot enough to maintain a magnetic field. It drifts toward our solar system from the direction of some distant nebula. As it approaches, the Sun's gravity pulls it in, accelerating it. It swings past the outer reaches of the Oort cloud, then plunges through the Kuiper belt. If it passes close enough to Neptune or Jupiter, it might get deflected, lose speed, and become trapped in a wide, tilted orbit. And there it stays, an icy Earth lurking just a few light days away, invisible to our telescopes because it's covered in dark, carbon-rich rock, reflecting almost no sunlight. But wait, if it's so dark and so far away, how do we even know it's there? That's the core question of the search for hidden planets, and we don't know for sure. The evidence is circumstantial. The clustering of distant Kuiper belt objects is real, but there are alternative explanations. For instance, the clustering could be a result of observational bias. Our surveys are most sensitive to certain parts of the sky, so we might only be seeing objects that look clustered because that's where we looked. More recent data from the Outer Solar System Origin Survey and the Dark Energy Survey have cast doubt on the original clustering signal, suggesting it may not be statistically significant. Yet other studies continue to find evidence for a slight bias-corrected alignment that still points to a massive perturber. Another alternative is that the clustering is caused by the gravitational influence of a massive disk of icy bodies, a dense inner Oort cloud, rather than a single planet. Simulations show that a disk of debris with a total mass of a few Earths could produce similar orbital alignments, but we haven't observed such a disk directly. Or it could be that the gravitational pull of passing stars over hundreds of millions of years has shepherded these distant objects into their current configuration. The solar system does not exist in isolation. It moves through the galaxy, and close stellar encounters are rare, but do happen. One study suggested that a star passing within 50,000 AU of the Sun could have perturbed the outer solar system enough to create the observed warp and clustering. But the most compelling alternative is that there is no hidden planet at all, and the anomalies are due to the Yarkovsky effect, a subtle force caused by the re-radiation of heat from small bodies that can change their orbits over millions of years. Or perhaps we simply haven't accounted for the influence of the known giant planets correctly. Neptune, for example, is a powerful gravitational sculptor, and its migration outward in the early solar system could have created many of the features we see today. So, Where does that leave us? The search for Planet 9 or Planet Y or a captured rogue is still active, and the methods used are fascinating, because we can't just look through a telescope and see a dark, distant world. We have to use indirect detection. The first method is orbital clustering analysis, which we've already discussed. The second is gravitational perturbation, measuring the tiny effects of a hidden planet on the orbits of known objects, like the Voyager spacecraft or trans-Neptunian binaries. A third method is direct imaging with the most sensitive telescopes, but that's like looking for a black marble in a coal cellar at midnight. The Japan Aerospace Exploration Agency's JAXA is planning a mission called the Outer Solar System Explorer that might fly through the region, but that's decades away. Right now, our best hope is the Vera C. Rubin Observatory in Chile. It's not just a telescope, it's a revolution. After more than 2 decades of planning, Rubin achieved first light in June 2025 and is now in full operation. Its Legacy Survey of Space and Time, LSST, began in early 2020. And over the next 10 years, it will image the entire visible southern sky every few nights. Its camera is the largest ever built for astronomy, 3,200 megapixels. It can capture objects so faint that they're barely visible, objects moving at the stately pace of a planet 150 AU away. If Planet Y exists, and if it happens to be in the southern sky, Rubin will find it, not by its brightness, but by its motion. A single pixel that shifts between exposures over weeks or months. It's like finding a needle in an infinite haystack, but the haystack is slowly being digitized. Of course, if we do find it, the first question will be, is it native or captured? That's where orbital characteristics come into play. A rogue planet captured by the Sun would have a very specific signature. Its orbit would be highly eccentric, very elongated, and likely inclined at a steep angle to the plane of the solar system. It would also have a slightly different composition than native solar system bodies. Rogue planets form in different stellar environments, so they might have different ratios of rock, ice, and metal. They might even have a different isotopic signature, the relative amounts of, say, carbon-13 or deuterium that would reveal their interstellar origin. If we could send a spacecraft to sample it, we could answer that question. But sending a spacecraft to a world 150 AU away, with a one-way light time of nearly 20 hours, is a monumental challenge. It would take decades. Still, there's another clue: the direction of the rogue's incoming path. If it came from a specific region of the sky, and if that region is free of young star-forming clusters or nearby stellar streams, it might hint at its origin. But the Sun has orbited the galaxy many times over its 4.6 billion-year lifetime. Any capture would have happened long ago, and the orbital information would be scrambled by the gravitational influence of other planets and passing stars. So, we may never know for sure. But let's think about what a captured rogue planet means for our solar system. For one thing, it would be the first proof that planets can be exchanged between stars. That would have profound implications for the possibility of life. If planets can be captured, then life might be able to hitch a ride, either in the form of extremophile microbes frozen inside a rogue's icy crust, or as a fully developed biosphere that survived the journey. The concept of panspermia, life spreading through the galaxy, would gain a whole new mechanism. And if that rogue world had a subsurface ocean kept liquid by tidal heating or radioactive decay, it might still harbor life today, a frozen Earth-like world with a hidden biosphere beneath kilometers of ice. On the other hand, a captured rogue could also be a threat. If it were on a highly elliptical orbit that brings it closer to the inner solar system every few thousand years, it could perturb the orbits of asteroids and comets, sending them careening toward Earth. That's a long-term hazard we'd have to monitor, but given the vast timescales, it's not something we need to worry about immediately. The real question is, why have we not found it yet? Part of the answer is the sheer difficulty of detection. At 150 AU, a rocky planet receives only about 1/10,000th of the sunlight that Earth gets. It's incredibly dim. Even with the most powerful telescopes, we can only see it if it reflects that light back at us. And if its surface is dark, like many outer solar system objects, its albedo could be as low as 0.04, meaning it reflects only 4% of the light that hits it. That makes it as dark as fresh asphalt. Now imagine trying to see a lump of asphalt 22 billion kilometers away. That's why the search has taken so long. But the search is not just about spotting a dot on a photo. It's about understanding the underlying forces that shaped our solar system. There are other anomalies that could point to a hidden planet. For instance, the orbits of some long-period comets, those coming from the Oort cloud, seem to have a preferential direction. That could be a signature of a massive perturbing body. There's also the question of the solar system's tilt. The Sun's equatorial plane is tilted about 7 degrees relative to the orbital plane of Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. That's called the obliquity of the ecliptic. It's a small but persistent misalignment that some astronomers think could be caused by a distant planet, or even a captured rogue, pulling on the inner system ever so slightly. But let's be honest, the evidence is not conclusive. The scientific community remains divided. There are passionate proponents of Planet 9, skeptics who favor a disk or stellar encounter explanation, and a growing number of researchers who think the answer might be a captured world from another star. Each hypothesis has its own strengths and weaknesses. Planet 9 from the formation disk can explain certain orbital alignments, but not the warp. A captured rogue can explain both if its mass and distance are right, but it requires a rare event. And the disk model requires an enormous amount of unseen debris that we haven't detected. So, how do we settle it? Observations. With the Vera Rubin Observatory coming online, we will have a decade of data. If there is a massive object out to 200 AU, we will see it, or we will not. If we see nothing, then the upper limits on the mass of a hidden planet become very strong. That doesn't rule out a smaller captured world, but it narrows the range. Conversely, if we see a faint moving dot, the hunt will shift from detection to characterization. We'll need follow-up observations with the James Webb Space Telescope, or the upcoming Extremely Large Telescope to study its spectrum, its surface composition, its thermal emission. But here's the exciting part. Even if we don't find a planet, the search itself is teaching us about the outer solar system. The Rubin survey will map the entire Kuiper belt and Oort cloud in unprecedented detail, revealing thousands of new objects. We'll learn about their orbits, their sizes, their colors. That data will help us test the cluster idea more rigorously. It might reveal dynamical families, groups of objects that share similar orbits because they were perturbed by the same event. And that event might be a stellar flyby, a migrating Neptune, or a hidden planet. In the end, The question isn't just about a rogue planet. It's about how dynamic and interconnected the galaxy really is. We tend to think of our solar system as a tidy, isolated collection of planets around a single star. But the reality is far messier. Planets migrate, comets are captured, and stars brush past each other every few million years. The boundary between our solar system and the rest of the galaxy is porous. Objects come and go. Stars steal planets from each other. And if the Sun did capture a rogue planet, it would be a reminder that we are not as alone as we think, not just in terms of life, but in terms of matter. The stuff of other star systems is mixed in with our own. So, did the Sun pull a rogue planet into the solar system? We don't know yet, but we're closer than ever to finding out. For the first time in history, we have the technological tools to answer this question. The next decade will be pivotal. We might discover a new planet, or we might close the book on Planet 9 forever. But either way, the journey is worth taking, because every time we look deeper into the darkness, we learn something new about where we came from and where we might be going. As you look up at the night sky, remember that what you see is just the surface. Most of the universe is invisible, dark, and waiting. Somewhere out there, in the cold beyond Neptune, a world may be circling our sun. A world that once belonged to another star. A world of ice and rock, of eternal twilight. A silent witness to the galaxy's long, slow dance. And we are only just beginning to hear its gravitational whisper. The question is, when we finally hear it clearly, will we recognize a long-lost sibling or a stranger from the deep? Let's find out. What do you think? Could there be a captured rogue planet hiding in our solar system? Let us know in the comments. And if you enjoyed this deep dive, consider subscribing for more explorations of the unexpected corners of our cosmic backyard. Thanks for watching, and I'll see you next time. But wait, there's one more thing before you go. We've talked about the search for a hidden world, the warp in the Kuiper Belt, and the tantalizing possibility that our Sun captured a rogue planet from interstellar space. But let's step back and look at the bigger picture. The story we just told is not just about one hypothetical planet. It's about how science evolves, how we piece together clues from the faintest signals, and how our understanding of the solar system changes every time we push the boundaries of observation. You see, the idea of a hidden planet isn't new. In fact, it's older than most people realize. The term Planet X was first used by Percival Lowell in the early 1900s to describe a hypothetical planet beyond Neptune that he believed was causing perturbations in the orbits of Uranus and Neptune. Lowell spent years searching for it, even building a dedicated observatory in Flagstaff, Arizona. He never found it, but his calculations were later used by Clyde Tombaugh, who in 1930 discovered Pluto, a tiny world that wasn't massive enough to explain the anomalies. Pluto became the 9th planet, but the discrepancies remained. Eventually, the Voyager missions gave us precise masses for the outer planets, and the perturbations vanished. Planet X was a ghost, but the name stuck. When Mike Brown and Konstantin Batygin proposed their evidence for a massive distant planet in 2016, they initially called it Planet 9, not Planet X, to avoid confusion with the historical search. However, the media and many astronomers still use Planet X as a catch-all for any undiscovered body beyond Neptune. This has led to some confusion, especially when you hear about Planet Y from the Princeton study. Y stands for why, as in why is the Kuiper belt warped? So the naming convention is messy. Planet X is the historical term. Planet 9 is the specific Caltech hypothesis for a Power 10 Earth mass world at 400 to 800 AU. And Planet Y is a newer, more localized hypothesis for a smaller rocky world at 80 to 200 AU. Why does this matter? Because the general public often hears Planet X and thinks of doomsday predictions or Nibiru. In reality, these are rigorous scientific hypotheses based on gravitational anomalies, not pseudoscience. But the line can blur when sensational headlines take over. That's why it's important to understand what the evidence actually says. And the evidence for a captured rogue planet is still circumstantial, but growing stronger with each new survey. Let's dig into the orbital characteristics that would mark a captured rogue. First, its orbit would be highly eccentric, likely an eccentricity above 0.8, meaning it swings from a close approach of perhaps 30-50 AU out to hundreds of AU. That's because a capture event usually robs the planet of energy, leaving it on a very elongated path. Second, its orbital inclination would be steep, maybe 30 to 60 degrees relative to the ecliptic plane. That's because the capture process randomizes the incoming direction. Native planets formed from the solar nebula have orbits that are nearly circular and low inclination, except for some scattered disk objects. A captured rogue would stand out like a sore thumb. Third, its composition might be different. Rogue planets form in other star systems where the mix of elements can vary. Some systems are rich in carbon, others in oxygen. If we could get a spectrum of a captured world, we might see an unusual ratio of ices, like more water ice than methane, or a higher fraction of silicates. There's even a chance it could have a thick atmosphere of hydrogen and helium if it's a gas giant. But our hypothesized Planet Y is smaller, so it might be a super-Earth with a thin atmosphere, or none at all. That would make it hard to detect spectroscopically, but not impossible with the James Webb Space Telescope. Now, one of the biggest criticisms of the captured rogue hypothesis is that capture events are extremely rare. Simulations suggest that less than 1% of rogue planets passing through the solar system would be captured into stable orbits. Most would just fly by or get ejected. But over the Sun's 4.6 billion year lifetime, thousands of rogue planets could have drifted through the Oort cloud. Even a 0.1% capture rate means we could have a few captured worlds out there. And we've only looked at a tiny fraction of the outer solar system. The probability is not zero, it's just uncertain. There's also the question of whether the Sun could capture a planet without disrupting the rest of the solar system. A large rogue passing close to Neptune or Jupiter could cause chaos. But if the capture happened early in the solar system's history, when the planets were still migrating and the disk was more massive, the effects might have been absorbed. Or, if the rogue is captured on a wide orbit far from the giant planets, it might not disturb them much. The observed warp at 80 to 200 AU is actually very delicate. A small disturbance could sustain it without wreaking havoc. So, what are the odds that Planet Y is a captured rogue versus a native world that formed in situ? The formation problem is severe. To form an Earth-sized planet at 100 AU, you'd need a very dense, cold region of the protoplanetary disk. Most models predict that the disk's surface density drops off sharply beyond 30 AU. Planetesimals would take billions of years to accrete that far out. Even Pluto took a long time. An Earth-sized body at 100 AU seems nearly impossible. So if planet Y exists, it almost certainly formed closer in and was scattered outward, or it was captured. The scattered scenario is more plausible within a single star system. A giant planet like Jupiter or Saturn, migrating inward or outward, could have ejected a smaller world into the far reaches. That's a well-known process in planetary dynamics. But why would that ejected world end up on a tilted, stable orbit? It's possible. For example, Neptune's migration in the Nice model kicked out many Kuiper Belt objects, some of which ended up in the scattered disk. A massive rocky world could have been ejected similarly, but then its orbit would likely be aligned with the plane, unless it was later tilted by a stellar flyby or another giant planet. So, the captured rogue hypothesis remains a strong contender. Another line of evidence comes from the galactic environment. The Sun is currently passing through a region of the galaxy called the local bubble, a cavity of hot gas carved by supernovae. This region is relatively empty, but as the Sun orbits the galactic center, it periodically passes through denser molecular clouds. These encounters can perturb the Oort cloud and send comets inward, but they can also trap rogue objects. Some researchers have suggested that the Sun's capture of a rogue planet might be more likely during these dense cloud crossings. The most recent such encounter may have occurred a few million years ago, too recent to have settled into a stable orbit. Actually, capture can happen quickly, within a few thousand years, and then the orbit would be stable over billions of years, if it's far enough. Now, let's talk about the search methods in more detail. I mentioned the Rubin Observatory, but there are other efforts underway. The Subaru telescope in Hawaii, with its wide-field camera, has been scanning the outer solar system for years. It's part of the Outer Solar System Origin Survey, OSSOS, which has discovered many trans-Neptunian objects. OSSOS data has been used to argue that the clustering of distant objects is not statistically significant after accounting for observational biases. But other surveys, like the Dark Energy Survey and the Pan-STARRS Survey, have found a marginal alignment that persists even after correction. The debate is far from settled. There's also the possibility of detecting a hidden planet via its thermal emission. Even though it reflects little sunlight, a planet at 150 AU would have a temperature of around 50 Kelvin. It would emit infrared radiation at wavelengths of 10 to 20 microns. The James Webb Space Telescope is sensitive to these wavelengths, but its field of view is tiny, like a pinhole compared to the sky. Searching an entire region of space with JWST would take centuries. However, if Rubin or another survey finds a candidate moving object, JWST can follow up to confirm and characterize it. Another clever method is to look for the gravitational effect on spacecraft. The Voyager probes, New Horizons, and the Pioneer spacecraft are all traveling through the outer solar system. Their trajectories are monitored very precisely using Doppler shift. Any slight deviation from the predicted path could indicate a hidden mass. So far, no anomalies have been found that require a new planet, but the sensitivity is limited. For a planet at 100-200 AU, the gravitational tug on a spacecraft would be tiny, on the order of micrometers per second per year. That's at the edge of detectability. There's also the proposed concept of a Planet 9 probe mission, like the one suggested by a team from the University of California. They proposed sending a small CubeSat with an ion thruster to the outer solar system, using gravity assists from Jupiter and Neptune to reach a trajectory that would allow it to measure the gravitational field. Such a mission could take 20 years to get out to 100 AU. It's not impossible, but it's expensive and requires long-term commitment. In the meantime, citizen science projects like Backyard Worlds and Planet 9 Patrol are enlisting the public to scan images from the WISE and NEO-WISE telescopes. These infrared surveys have covered most of the sky. If Planet Y is warm enough to emit detectable infrared radiation, it might have been captured in those images. But the data is massive, and automated algorithms can miss moving objects that are very faint. Human eyes are still better at spotting anomalies. That's how the brown dwarf WISE 0855 was discovered in 2013. It was a faint blob that a citizen scientist flagged. So, your own computer could help find a hidden planet. But let's step back to the big question: why does any of this matter? Beyond the thrill of discovery, finding a captured rogue planet would revolutionize our understanding of planet formation. It would prove that planets can be exchanged between stars, which has implications for the frequency of habitable worlds. If planet swapping is common, then life could spread through the galaxy more easily than we thought. It also raises the question, could the Earth have been? Right now, as you read these words, a small spacecraft is hurtling through a region of space so empty and so cold that it defies human intuition. The temperature of the surrounding interstellar medium is just a few degrees above absolute zero, minus 270 degrees Celsius. That's the point where atoms themselves almost stop vibrating. And Voyager 1 has been out there for 49 years. It launched in 1977. It has traveled more than 24 billion kilometers from Earth. It crossed the boundary of our solar system, the heliopause, over a decade ago. And right now, it still works. It still sends signals. It still talks to us. How? How does a machine built in the 1970s survive the most hostile environment in the known universe for half a century without freezing solid? The answer is not what most people expect. And it's more fascinating and more counterintuitive than you might think. Because here's the first thing you need to understand. The real question isn't whether Voyager can survive the cold of space. The real question is whether you understand what cold in space actually means. When you step outside on a winter morning and feel the cold bite your face, a very specific physical process is happening. Air molecules, billions upon billions of them, are colliding with your skin. Each collision carries heat away from your body. The more collisions, the faster you lose heat. The faster you lose heat, the colder you feel. That's conduction. It requires contact. It requires matter. Space has almost none. In the interstellar void where Voyager 1 travels right now, there are roughly a few atoms per cubic centimeter. Compare that to the air in this room, around 10 billion molecules per cubic centimeter. The difference is almost incomprehensible. With so few particles to collide with, heat cannot conduct away. There is no medium to rob warmth from a spacecraft the way winter air robs warmth from your face. So, how does heat escape in space? Only one way: radiation. Every object with a temperature above absolute zero emits heat as infrared radiation, invisible light that travels outward in all directions. In space, that's the only way heat moves, and radiation is slow, gradual, manageable. Think of it this way. In a cold room, a cup of coffee cools quickly because air is constantly stealing heat from the ceramic. Put that same cup in a vacuum, say inside a thermos, and it cools far more slowly, radiating heat outward like a dimming lamp. Voyager 1 is that cup of coffee floating in a vacuum so deep that heat can only escape one way. That changes everything. The cold of deep space isn't aggressive. It doesn't attack. It simply waits for your heat to bleed away. And if you generate heat fast enough, you survive. Voyager doesn't have solar panels. That's not an accident. The engineers at NASA knew exactly where this spacecraft was going. At the distance of Jupiter, sunlight is already 25 times weaker than on Earth. At Saturn, even more. By the time Voyager crossed into interstellar space, solar panels would have been useless. Cold, dark, dead weight. So, they chose something else. Plutonium-238. Voyager carries 3 radioisotope thermoelectric generators, RTGs. These devices work on a principle almost poetic in its simplicity. Plutonium-238 decays radioactively, and that decay releases heat, constantly, automatically, without fuel, without combustion, without sunlight. That heat passes through thermoelectric converters, materials that generate electricity when one side is hot and the other is cold. No moving parts, no switches, no maintenance required. When Voyager launched in 1977, its RTGs produced around 470 watts of power, enough to power several light bulbs. Modest, but sufficient for a spacecraft designed to be ruthlessly efficient. But the RTGs do more than generate electricity. They generate heat. And in the cold of space, heat is survival. The warmth produced by the RTGs radiates through Voyager's systems, keeping electronics, cables, and instruments within operational temperature ranges. Even the electronics themselves, every circuit that fires, every calculation that runs, produces residual heat that contributes to keeping the spacecraft alive. It's a closed loop of warmth in the middle of an infinite freeze. But warmth alone isn't enough. You also have to keep it. Imagine wrapping something in a blanket so advanced that it reflects heat back at itself. A blanket so thin it weighs almost nothing. A blanket designed not for comfort, but for survival at the edge of the solar system. That's what covers Voyager. Multi-layer insulation, MLI, is a technology built from ultra-thin sheets of mylar and captain, layered together with gaps of near vacuum between them. Each layer reflects infrared radiation. Each gap prevents conduction. Together, they create a thermal barrier that slows heat loss to a crawl. Voyager is wrapped in this material like a gift sealed against the universe. But here's the engineering challenge that most people don't consider. The problem wasn't just keeping Voyager warm, far from the sun. The problem was keeping Voyager from overheating near the sun. In the early years of the mission, during the flybys of Jupiter and Saturn, the spacecraft was relatively close to our star. The RTGs were running at full power. The electronics were generating heat, and sunlight, while weaker than at Earth, was still a factor. Engineers had to design a thermal system that could handle both extremes, the warmth of the inner solar system and the deep freeze of interstellar space. A balance struck with layers of insulation, thermal louvers, and radiators that could vent excess heat when needed. It worked. Decades later, in temperatures approaching absolute zero, Voyager's core systems still operate within their design parameters. A thermos in the void, engineered to survive anything. Let's dig deeper into that thermal balancing act. The RTGs themselves are not just power sources, they are heat sources. Each RTG contains about 4.5 kilograms of plutonium-238 oxide. That plutonium decays by alpha emission, releasing particles that collide with the surrounding material and produce heat. At the time of launch, each RTG generated about 1,500 watts of thermal heat, of which roughly 160 watts were converted to electricity. The rest, over 1,300 watts per RTG, was waste heat. That waste heat was not a problem. It was a necessity. It kept the spacecraft warm. But during the Jupiter and Saturn encounters, the combination of that waste heat plus solar heating could have pushed temperatures too high. So Voyager was equipped with thermal louvers, movable panels that act like blinds. When the spacecraft was too hot, the louvers opened to allow heat to radiate away into space. When it was too cold, they closed, trapping the heat inside. These louvers are passive. They use bimetallic springs that expand or contract with temperature, no motors, no electronics. They have been opening and closing for nearly 50 years without failure. That's the kind of engineering that makes Voyager extraordinary. And then there's the RTG's heat output over time. Plutonium-238 has a half-life of about 88 years. That means every 88 years, half of the remaining plutonium decays into lead, and the heat output drops by half. The process is slow, but it's relentless. Since 1977, Voyager's RTGs have lost roughly 40% of their original power output. What started at 470 watts now produces somewhere around 250 to 260 watts, and it drops by approximately 4 watts every year. That power decline affects everything. Less electricity means less heat from the electronics. Less overall thermal energy means the spacecraft's internal temperature slowly drops. NASA has been managing this decline carefully, systematically, ruthlessly. Over the decades, they have powered down systems one by one to keep the most critical instruments alive. Cameras, long since off. Certain science instruments, deactivated. Heaters for non-essential components, switched off, allowing some parts of the spacecraft to cool and partially freeze, as long as the core keeps functioning. It's a managed death, slow, deliberate, and inevitable. But here's the key insight that often gets overlooked. The reason Voyager hasn't frozen after 49 years is not just because it has a heat source. It's because the heat source is perfectly matched to the heat loss rate. In a vacuum, the only way heat leaves is by radiation. The rate of radiative heat loss depends on the surface area and the temperature of the spacecraft. Voyager's surface is covered with that multi-layer insulation, which has an extremely low emissivity. It barely radiates heat away. Meanwhile, the RTGs continuously supply a steady stream of thermal energy. Over time, the spacecraft reaches an equilibrium temperature, where the heat generated equals the heat radiated. That equilibrium temperature, thanks to the insulation and the RTG output, is well above the freezing point of the electronics. As the RTG power decays, the equilibrium temperature slowly drops. But because the heat loss also decreases as the spacecraft cools, since radiation is proportional to the fourth power of temperature, the system self-regulates to some extent. It's a beautiful, elegant balance. Now, let's talk about what Voyager actually experiences in interstellar space. In August 2012, something historic happened. Voyager 1 crossed the heliopause. You may not know that word, but it describes one of the most important boundaries in our cosmic neighborhood. The heliopause is the edge of the heliosphere, the vast bubble of solar wind and magnetic influence that our sun projects outward in all directions. Inside the heliosphere, the sun's particles flow and interact with everything. Outside it, the sun's reach ends. Voyager 1 became the first human-made object to cross that line to enter true interstellar space. The environment changed immediately. The solar wind, a constant stream of charged particles from the sun, stopped. The magnetic field around the spacecraft shifted. The radiation environment became dominated not by our sun, but by the rest of the galaxy. And the temperature of the surrounding medium dropped even further. In the heliosphere, the tenuous plasma can be surprisingly hot, millions of degrees in some regions, though so sparse it transfers almost no heat to anything. Beyond the heliopause, the interstellar medium is colder and denser, still impossibly thin by Earth standards, but different. Voyager crossed into this region and kept going. The RTGs kept producing heat. The MLI kept trapping it. The thermoelectric generators kept converting it into power. A machine built in California in the 1970s, operating in a region of space no human instrument had ever reached, functioning exactly as designed. There is something almost defiant about it, but we need to clear up a common misconception. Voyager left the solar system. It crossed the heliopause, but it has not left the galaxy. The solar system is just a tiny suburb of the Milky Way galaxy. The galaxy is 100,000 light-years across. Voyager has traveled about 0.002 light-years. It will take tens of thousands of years to even approach another star. So when you hear Voyager left the solar system, that's correct. When you hear Voyager left the galaxy, that's false. It's still well within the galactic disk, surrounded by the sparse gas and dust of the interstellar medium. The cold it experiences is not the cold of intergalactic space. That would be even colder, close to absolute zero. The cold of interstellar space is still extreme, but not quite as extreme as the void between galaxies. And this brings us to the engineering philosophy behind Voyager. This spacecraft was built in an era when NASA didn't think in terms of planned obsolescence. There was no profit motive to make things fail after a few years. The goal was to build something that would work for as long as possible, because the mission was designed to explore planets that were billions of kilometers away, and the journey would take decades. The engineers at the Jet Propulsion Laboratory in Pasadena, California, knew that once Voyager left Earth, there would be no repair missions, no upgrades, no second chances. So they built it with redundancy, with margins, with components that were tested to extremes. They used gold-plated connectors to prevent corrosion. They used radiation-hardened electronics. They designed the RTGs to last for decades. They wrapped the spacecraft in that multi-layer insulation with a calculated lifespan. They even pre-programmed the computer to handle certain failures autonomously. The result is a machine that has outlived every expectation. It was designed for a 4-year primary mission to Jupiter and Saturn. It is now in its 49th year. That's not luck. That's deliberate, over-engineered, long-term thinking. Contrast that with the modern world of consumer electronics. Your phone's battery degrades after 2 years. Your laptop's software becomes obsolete. Cars are designed with parts that fail just outside the warranty period. Planned obsolescence is baked into the economy. But Voyager represents the opposite philosophy. Build it to last, because the mission is worth it. And that philosophy extends to the very heat source. Plutonium-238 is not something you can just buy off the shelf. The United States stopped producing it in the 1980s. For a time, NASA had to rely on stockpiles from the Cold War. The RTGs on Voyager were fueled with plutonium that was produced decades before the spacecraft was even built. And that plutonium is still decaying, still providing heat, still keeping the spacecraft alive. It's a remarkable feat of resourcefulness and foresight. But nothing lasts forever. Current estimates suggest the last science instruments will go silent somewhere between 2025 and 2030. Some may already be offline by the time you watch this. And when the final systems lose power, when there is no more electricity to run the transmitter, no more warmth to protect the circuits, Voyager will begin to truly freeze. Not because space suddenly became colder, but because the source of heat is gone. The insulation will still be there by the mylar and captain still wrapped around the frame, but they can only slow the inevitable. Without the RTGs, the heat bleeds away into the void. Slowly at first, then completely. The death of Voyager won't be an explosion. It won't be a collision or a failure or a dramatic final transmission. It will be silence. One instrument going dark, then another. Then the transmitter itself. One last signal crossing 25 billion kilometers of empty space, taking over 21 hours to reach Earth. And then, nothing, just silence. But here is what stops you cold when you really think about it. Voyager doesn't stop. In space, there is no friction, no air resistance, no force to slow a moving object down. Newton's first law applied at cosmic scale. An object in motion stays in motion. Voyager 1 is currently traveling at approximately 17 kilometers per second. That's over 61,000 kilometers per hour. And when its last system goes dark, when the final signal fades, when the spacecraft is nothing more than frozen metal and exhausted plutonium drifting in the interstellar medium, it will still be going 17 kilometers per second. In roughly 40,000 years, Voyager 1 will make a close approach to a star called Gliese 445, a small red dwarf in the constellation Camelopardalis. Not a collision, just a pass. The closest it will come to another star since leaving our solar system. No one alive today will know when it happens. There will be no signal to confirm it. No instrument to record it. Just a frozen spacecraft drifting past a distant star in the darkness, carrying a golden record with the sounds and images of a civilization that existed briefly on a small planet around an average star, a fossil traveling forever. Think about what that means. Voyager was never designed to last this long. It was designed to go, to reach Jupiter, Saturn, the edge of the solar system, and keep going. The durability wasn't the goal. The journey was. And yet, here we are, nearly 50 years later, still listening, still receiving data from a machine smaller than a school bus, operating on less power than a light bulb, in conditions that would destroy almost anything humanity has ever built. It didn't freeze because we understood the cold. Not just the temperature, but what cold in space actually means. The absence of conduction, the slowness of radiation, the way heat behaves when there is almost nothing around to take it. We gave Voyager a heartbeat of plutonium and wrapped it in the thinnest armor imaginable, and it flew. It's still flying. But there's another layer to this story that often gets missed. The reason Voyager hasn't frozen isn't just about the RTGs and the insulation. It's also about how the spacecraft manages its internal heat distribution. You see, even with the RTGs producing heat, that heat doesn't spread evenly. Some parts of the spacecraft, like the high-gain antenna, are exposed directly to the cold of space. Others, like the electronics bay, are tucked inside the insulation. Engineers had to design a system of heat pipes and conductive pathways to move warmth from the RTGs to the critical components. They also had to make sure that certain parts, like the propellant lines for the thrusters, didn't freeze. These lines carry hydrazine, a fuel that freezes at around 2 degrees Celsius. If the hydrazine freezes, the thrusters can't fire, and Voyager can't orient itself to point its antenna at Earth. So the RTG waste heat is carefully routed to keep the propellant lines warm. That's why you sometimes hear about heaters being turned off to save power. Those heaters are actually electric resistance heaters that supplement the RTG heat. As power dwindles, the heaters are the first things to go, because the engineers know that the RTG waste heat alone might still be enough to keep the propellant from freezing, at least for a while. And then there's the power management itself. The RTGs produce direct current at a low voltage, around 30 volts. That voltage has dropped over time as the plutonium decays. The electronics on Voyager were designed to operate within a certain voltage range, and as the voltage falls, the equipment becomes less efficient and more prone to failure. NASA has been able to compensate by switching to backup systems that can tolerate lower voltages, but eventually the voltage will drop too low to power the transmitter. That's the end game. When the power output falls below about 200 watts, the spacecraft can no longer maintain communication. Some estimates put that threshold around 2025 to 2030, but it could be later if the electronics continue to degrade gracefully. Now, I want to take a moment to appreciate the sheer audacity of the Voyager mission. In 1977, the personal computer was barely a concept. The most advanced microprocessors were still years away. Voyager's computer, the command and data system, had a memory of 69 kilobytes. That's less than a single page of text on your smartphone. It used magnetic core memory, where each bit was stored by magnetizing a tiny ring of ferrite. It was programmed in a custom assembly language. And yet, that computer has been running for nearly half a century, navigating through the solar system, executing complex sequences of commands, and returning scientific data from the edge of interstellar space. It has survived multiple glitches, including a famous incident in 2010 where a single bit flip in the memory caused the spacecraft to start sending garbled telemetry. Engineers managed to diagnose and fix the problem from Earth, sending a command to reset the affected memory cell. That's like performing brain surgery on a patient 17 light hours away. The thermal system is similarly resilient. The multi-layer insulation is not a single blanket, but dozens of layers, each one carefully designed to reflect infrared radiation. The outer layer is often made of a material that is electrically conductive to prevent static charge buildup. The inner layers are separated by lightweight spacers to create vacuum gaps. But here's the surprising part. The insulation actually works better as it ages. Over time, the layers settle closer together, but the vacuum between them remains. The reflectivity of the mylar can degrade slightly due to cosmic ray bombardment, but the overall thermal performance has remained remarkably stable. Voyager's internal temperature, measured by onboard sensors, has dropped only a few degrees over the past 4 decades. The spacecraft's heart, the electronics bay, stays around 10 to 20 degrees Celsius, a comfortable room temperature, even though the hull outside is near absolute zero. And what about the RTGs themselves? They are not just simple boxes of plutonium. Each RTG is a complex assembly of thermocouples, semiconductor junctions that convert heat into electricity. These thermocouples are made of silicon-germanium alloys, chosen for their ability to withstand high temperatures and radiation. The hot side of each thermocouple is in contact with the plutonium fuel, which glows red hot at about 1,000 degrees Celsius. The cold side is connected to the spacecraft's structure, which radiates heat into space. That temperature difference, nearly 1,000 degrees, drives the electric current. Over time, the thermocouples degrade due to thermal cycling and radiation damage. Their efficiency drops. That's another reason the power output decreases faster than the plutonium decay alone would predict. But even with that degradation, the RTGs have performed far beyond initial expectations. They were designed for a 5-year mission. They've lasted nearly 50. So, when we ask why Voyager hasn't frozen, the answer is multifaceted. It's the combination of a heat source that never stops, a thermal blanket that traps that heat, a clever system of louvers and heat pipes that balance temperature, and an engineering philosophy that prioritized longevity over cost. It's also the physics of heat transfer in a vacuum, the fact that without conduction or convection, heat can only radiate away slowly. Voyager is essentially a very efficient thermos, and the cold of space is a very patient thief. But there's one more factor that often goes unmentioned: the spacecraft's orientation. Voyager 1 is kept pointed toward Earth using its thrusters, which fire small bursts of hydrazine to adjust its attitude. Those thrusters also produce heat when they fire, albeit very briefly. More importantly, the spacecraft's antenna is always aimed at our planet, which means the backside of Voyager, the side facing away from Earth, gets colder than the front side. Engineers have to account for that asymmetry. They've designed the thermal control system to ensure that even the coldest parts of the spacecraft stay above the minimum operating temperature. And they've done this with no active heaters in many cases, relying solely on the passive heat distribution from the RTGs. I want to emphasize something about the concept of freezing in space. When we say something freezes, we usually mean water turning into ice. But there's no water on Voyager, at least not in its electronics. The danger is not ice formation, but rather the failure of electronic components at low temperatures. Semiconductors become less conductive when cold, and certain materials become brittle. Solder joints can crack. Capacitors can lose their charge. The real enemy is the differential expansion of materials. As different parts cool at different rates, they can warp and break. Voyager's engineers designed the spacecraft to handle those stresses by using materials with similar coefficients of thermal expansion and by leaving gaps where necessary. The result is a machine that can withstand temperature swings of hundreds of degrees without self-destructing. Now, let's look ahead. The RTGs will continue to decay. The power will continue to drop. Eventually, the voltage will fall below the threshold needed to run the transmitter's amplifier. That will be the end of communication. But the spacecraft itself will continue on its trajectory, a silent monument to human curiosity. In the distant future, perhaps 1 billion years from now, Voyager will have traveled so far that it will be no closer to any star than it is now, just drifting in the void. It will be a ghost ship, frozen and dead, yet still carrying the golden record, a time capsule of Earth's culture, music, and greetings in 55 languages. The record is made of copper and gold, designed to last for billions of years in the vacuum of space. The grooves are microscopic. The cover includes a map of pulsars that pinpoints Earth's location in the galaxy. It's a message in a bottle, cast into the cosmic ocean. And that brings us back to the original question. Why hasn't Voyager 1 frozen after 49 years in space? Because we built it to survive. Because we understood that the cold of space is not an active force, but a passive absence of heat. Because we gave it a furnace of plutonium, wrapped it in a mirror blanket, and set it on a course that would take it farther than any object we've ever made. It didn't freeze because it was never meant to freeze. It was meant to keep going for as long as it could, and it has. When the last signal comes, and it will come, probably within this decade, what exactly are we losing? A spacecraft, a science instrument, a piece of 1970s engineering, or the last physical proof that a small, curious species looked up at the stars, built the best thing it knew how to build, pointed it at the unknown, and let it go? Maybe the answer is all of the above. Maybe that's enough. But there's something else to consider. Voyager is not alone. Its twin, Voyager 2, is still operational as well, on a different trajectory. It left the heliosphere in 2018. It's still sending back data from interstellar space. Together, the two Voyagers represent the farthest reaches of human presence. They are our ambassadors. And when they finally fall silent, we will have lost a direct connection to the cosmos. No other spacecraft will be able to replace them for decades. The New Horizons probe, which flew past Pluto in 2015, is still active and heading out, but its RTG will last perhaps another 15 years. The Voyagers are the last of their kind, nuclear-powered, long-lived, and incredibly capable. So when you hear that Voyager 1 hasn't frozen, remember that it's not just about temperature. It's about a philosophy of building things that outlast their builders. It's about the audacity to send a message that will outlive our species. It's about the fact that in the vacuum of space, the only way to survive is to generate your own heat. And we gave that machine the ability to do so for half a century. It has not frozen because we refuse to let it freeze. And that, perhaps, is the most human thing about it. And that, perhaps, is the most human thing about it. But let's step back for a moment and examine the specific engineering decisions that made this defiance possible, because the story of Voyager's survival isn't just about the big systems, the RTGs, and the multi-layer insulation. It's also about the tiny, almost invisible choices that add up to an unbreakable whole. Consider the thermal louvers I mentioned earlier. These are not complex motorized shutters. They are simple, passive spring-loaded blades that open and close based on temperature. When the spacecraft is warm, the blades pivot open, allowing heat to radiate away through a radiator panel underneath. When the spacecraft cools, the blades close, trapping the heat inside. No electricity required, no computer command, just a bimetallic strip that bends as it heats or cools, actuating a tiny mechanism that has been opening and closing reliably for nearly 50 years. It's a piece of 1970s mechanical engineering that has never needed maintenance, and it never will, because there's no one to maintain it. Now, think about what that means. On Earth, a simple door hinge can wear out after a few thousand cycles. A bimetallic strip in a household thermostat can drift out of calibration over decades. But in the vacuum of space, with no humidity, no dust, no corrosive atmosphere, and no mechanical fatigue from gravity, these louvers operate in a near-perfect environment. They don't wear out because there's almost nothing to wear them out. The only degradation comes from cosmic rays and the occasional micrometeorite impact, but those are statistically negligible over the mission's lifetime. So, the louvers keep working, silently regulating the spacecraft's temperature with a precision that would make a modern thermostat proud. And that brings us to another critical but often overlooked component, the propellant tanks. Voyager carries hydrazine for its thrusters, as I noted earlier. But hydrazine is not just any fuel. It's a monopropellant, meaning it decomposes exothermically when passed over a catalyst. That decomposition produces hot gas, which is expelled through the thruster nozzles to provide thrust. The hydrazine itself must be kept from freezing, which is why the propellant lines are routed near the RTGs. But there's a catch. The hydrazine tank is mounted on the side of the spacecraft, away from the main heat source. Engineers had to calculate exactly how much heat would conduct through the tank's mounting brackets and how much would radiate from the nearby RTG. They determined that with the MLI covering the tank, the hydrazine would remain above its freezing point for the entire mission, assuming the RTGs kept producing enough heat. And indeed, it has. The tank temperature has only dropped a few degrees since launch. The propellant is still liquid, still ready to flow when the thrusters need to fire. But here's the truly remarkable part. The thrusters themselves are not heaters. They are cold start capable, meaning they can ignite even when the catalyst bed is at extremely low temperatures. That capability was built in from the start, because engineers knew that after decades in space, the thrusters would be cold. They designed the catalyst bed with a special coating that allows the hydrazine to ignite even when the bed is at 50 degrees Celsius or lower. And it works. Voyager still fires its thrusters occasionally to adjust its orientation, and each burn warms the catalyst bed slightly, keeping it from freezing permanently. Now, let's talk about the golden record again, because it's more than just a cultural artifact. It's a thermal design element. The record is mounted on the side of the spacecraft, exposed to space. It's made of copper, gold, and aluminum, with a cover that can be removed by an alien civilization. But the record itself is not heated. It's allowed to reach the ambient temperature of interstellar space, which is near absolute zero. That means the record is effectively frozen. But here's the thing. The materials used in the record, gold, copper, and aluminum, are chosen for their durability at cryogenic temperatures. They don't become brittle. They don't crack. The grooves that encode the images and sounds are etched into the metal, and they will remain readable for billions of years, even at 270 degrees Celsius. So, when we say Voyager hasn't frozen, we're talking about its electronics and instruments. The golden record is frozen, and it's perfectly fine. This dual reality, some parts of the spacecraft are cold, some are warm, is a testament to the thermal engineers who designed the system. They didn't need to keep every single component at room temperature. They only needed to keep the critical ones warm. The electronics, the transmitter. Right now, you are sitting inside a structure so large that light itself needs 20,000 years to travel from one end to the other. That is not the Milky Way. It is not a galaxy cluster. It is something most people have never seriously thought about. It is the spiral arm you live in. The Orion arm is the local region of the Milky Way that contains our sun, our planets, and every single star you have ever seen with your naked eyes. It stretches across distances so vast that our entire solar system is barely a speck buried inside it. For decades, scientists dismissed it as a minor spur, a small and unimpressive offshoot connecting more important structures. New evidence says they were wrong. The arm is enormous, and we are lost inside it. Ask someone where they live in the universe, and they will probably say, Earth. Push them further, and they might say the solar system. Push harder, and they will eventually say the Milky Way. That answer feels complete. It sounds like it covers the full picture. Earth, solar system, Milky Way. 3 steps from your front door to the cosmos. Done. But that answer skips something enormous. Between the solar system and the full Milky Way sits a structure so vast that most people have never even considered it. A structure large enough to contain every star you have ever seen in the night sky. A structure that stretches at least 20,000 light-years from end to end and spans roughly 3,500 light-years across. A structure that holds billions of stars, massive clouds of gas and dust, stellar nurseries where new suns ignite, and the scattered remnants of stars that died before our planet even existed. That structure is the Orion Arm. It is the spiral arm of the Milky Way where our solar system actually sits. Not the galaxy as a whole, not some vague region labeled near the center or out on the edge. A specific, physical, mappable piece of galactic architecture with defined boundaries, a measurable width, a traceable length, and an internal structure complex enough that scientists have spent decades trying to understand it from the inside. The strange part is how invisible it feels. The Orion Arm does not announce itself when you look up at the sky. You cannot point to it the way you can point to the moon or a bright planet. You cannot see its edges. You cannot sense its shape. You are inside it right now. You have been your entire life, and you will be for as long as humanity exists on this planet. It surrounds you completely. Every direction you look through the night sky, you are looking through some portion of the Orion Arm's gas and stars and dust. You are embedded in it the way a single cell is embedded inside an organ. The cell cannot see the organ. It does not know the organ's shape. It only knows its immediate surroundings. That is exactly the problem astronomers have faced for over a century. We live inside a spiral arm of a galaxy, and for most of human history, we had no idea the arm was even there. The Milky Way is a barred spiral galaxy. From above, if you could somehow hover 100,000 light-years overhead and look down, you would see a flattened disk of stars and gas, organized into sweeping curved arms radiating outward from a central bar-shaped core. The galaxy contains somewhere between 200 billion and 400 billion stars. It spans roughly 100,000 light-years from edge to edge, possibly more depending on how you define the faint outer regions. It rotates. It has structure, and within that structure, the stars and gas are not spread evenly. They concentrate along arms. The Milky Way has 2 confirmed major spiral arms: the Perseus Arm, which lies farther from the galactic center than we are, and the Scutum Centaurus Arm, which wraps around closer to the core. There are also several minor or intermediate arms, and the picture keeps getting revised as better data arrives. The galaxy's spiral architecture is one of the hardest things in astronomy to pin down, precisely because we are sitting inside the disk, trying to map a pattern we cannot step outside of to see. The Orion Arm sits between 2 of these larger structures. On the side, closer to the galactic center, lies the Sagittarius Arm, sometimes called the Carina Sagittarius Arm. On the side farther from the center lies the Perseus Arm, one of the galaxy's 2 dominant spiral features. The Orion Arm bridges the gap between them, running roughly parallel to both, slightly diagonal, stretching from the direction of the constellation Cygnus on one end toward the direction of the constellation Carina on the other. For a long time, astronomers treated it as worth mentioning. The standard picture of the Milky Way labeled it as a spur, a small offshoot connecting bigger arms. Galaxy diagrams drew it as a minor feature. Textbooks described it almost apologetically. Just a local spur, a minor bridge, nothing compared to the real arms. That turned out to be wrong, but we need to understand why before we can appreciate the full scale of what we are dealing with. First, you need to understand where you actually are inside this thing. The solar system sits near the inner rim of the Orion Arm, not at the center, not at the outer edge. Close to the side that faces the galactic core, roughly halfway along the arm's total length. Our Sun orbits the center of the Milky Way at a distance of approximately 26,000 light-years, placing us roughly halfway from the galactic center to the disk's outer edge. We are not in the bustling downtown core of the galaxy. We are more like a quiet suburb, far removed from the intense radiation and gravitational chaos near the central bar and the supermassive black hole that sits at the heart of everything. From our position, the nearest edge of the Orion Arm's inner boundary is only a few hundred light-years away. The outer edge of the arm lies roughly 3,000 light-years in the opposite direction. If you could somehow see the arm in cross-section, our Sun would appear near one wall of a wide corridor of stars and gas, slightly off-center, tucked into a relatively thin region of the arm's overall width. But even that description understates the situation, because the solar system is not just near the inner rim. It is inside a specific cavity within the arm called the local bubble. The local bubble is a region of space approximately 1,000 light-years across, where the density of interstellar gas is dramatically lower than the surrounding material. It was carved out roughly 14 million years ago by a series of supernova explosions from massive stars in the nearby Scorpius-Centaurus stellar association. Those explosions blasted away the local gas and dust, creating a hot, diffuse cavity that our solar system now drifts through. The interior of the bubble reaches temperatures around 1 million degrees Kelvin, but the gas is so thin that individual hydrogen atoms can be separated by distances measured in miles. The bubble is not a void in the ordinary sense. It is more like a region where the interstellar medium has been heated and thinned to near irrelevance. Think of it this way. The Orion Arm is like a vast forest stretching thousands of light-years in every direction. Dense clouds of molecular gas form the thickest groves. Bright young stars blaze in clearings where the canopy has been blown open by stellar winds and explosions. And the local bubble is a small meadow within that forest, a pocket of relative emptiness where the trees thin out and the view opens up. Our solar system sits in that meadow. We can see the surrounding forest from where we stand, but the forest extends so far in every direction that its true boundaries vanish beyond what we can observe. That meadow, the local bubble, is 1,000 light-years wide. It sounds enormous. By any human standard, it is enormous. Light takes 1,000 years to cross it. If you could drive a car at highway speed across the local bubble, the journey would take roughly 11 billion years, far longer than the current age of the universe. The local bubble is incomprehensibly vast by the measure of human experience, and it is a tiny clearing inside the Orion Arm. The arm itself is roughly 3.5 times wider than the local bubble, and at least 20 times longer. The bubble occupies a small fraction of the arm's total volume. You could fit dozens of local bubbles side by side across the arm's width and hundreds along its length. The cavity we call home, the region of space that contains every star visible to the naked eye from Earth, every constellation humans have ever named, every nearby stellar system we have ever studied in detail, is a small pocket inside a much larger galactic feature that most people have never seriously considered. This is where the first jolt of scale hits. Everything familiar in the night sky lives inside the Orion Arm. Sirius, the brightest star in our sky, sits about 8.5 light-years away. It is inside the arm. Vega, the bright blue star almost directly overhead in northern summer skies, lies about 25 light-years away. Inside the arm, Proxima Centauri, the nearest known star to our Sun at just over 4 light-years distant, is obviously inside the arm. So is every star in the Big Dipper, every star in Orion's belt, every star in Cassiopeia. Every single point of light you can resolve with your unaided eyes on even the clearest, darkest night belongs to the Orion Arm. The stars that form the constellation Orion itself are actually scattered across a wide range of distances within the arm. Betelgeuse, the red supergiant marking Orion's shoulder, sits roughly 700 light-years from Earth. Rigel, the blue supergiant at Orion's foot, lies about 860 light-years away. The 3 stars of the belt range from roughly 800 to over 1,000 light-years distant. All of them are inside the Orion Arm. All of them are part of the same galactic structure that holds our Sun. They are not close neighbors in any meaningful sense. Some of them are separated from us by distances that light takes centuries to cross. But on the scale of the arm itself, they are practically next door. They are all embedded in the same local stretch of the same spiral feature. And this is what most people miss entirely. When you look up at the night sky and see thousands of individual stars scattered across the darkness, you are not seeing the Milky Way in general. You are seeing the inside of the Orion Arm. The band of soft light that stretches across the sky on clear dark nights, the thing we casually call the Milky Way, is the combined glow of billions of distant stars concentrated in the galactic disk. But the individual bright stars you can pick out with your eyes are almost entirely local. They are your neighbors within the arm. The night sky is not a window onto the galaxy. It is a view from inside one specific piece of it. This is the first clue that the Orion Arm is not a minor feature. It is large enough to contain every object that has ever felt close and familiar in the human sky. Now, consider what else is in there. The Orion Nebula, one of the most photographed objects in all of astronomy, sits roughly 1,340 light-years from Earth. It is a massive stellar nursery where new stars are actively forming right now. Illuminated by a cluster of hot young stars called the trapezium at its core, the nebula spans about 24 light-years across and contains enough gas and dust to form thousands of new stellar systems. It is one of the nearest large star-forming regions to our planet, and it is inside the Orion Arm. The Cygnus X region, one of the richest star-forming complexes in the entire Milky Way, lies roughly 4,600 light-years away in the direction of the constellation Cygnus. It contains some of the most massive and luminous stars known, embedded in enormous clouds of molecular hydrogen that stretch across hundreds of light-years. For years, the distance to Cygnus X was uncertain, and some astronomers believed it might belong to the more distant Perseus Arm. Precise radio measurements revealed the truth. Cygnus X is inside the Orion Arm. It belongs to our structure. The Taurus molecular cloud, a quieter but closer region of active star formation, sits about 440 light-years away. The Rho Ophiuchi cloud complex, another stellar nursery glowing with infrared light from embedded young stars, lies roughly 460 light-years distant. The Vela molecular ridge, a chain of dense gas clouds where stars are being born across a stretch of several hundred light-years, lives inside the Arm. The Cepheus star-forming region is inside the Arm. The North American Nebula, a striking cloud of ionized hydrogen roughly 1,600 light-years away, that gets its name from its shape resembling the continent, is inside the Arm. All of these objects, every one of them, exist within the same galactic structure that holds our Sun. They are not scattered randomly through the Milky Way. They trace the internal anatomy of the Orion Arm, marking places where gas has piled up densely enough for gravity to win its slow battle against thermal pressure and ignite new generations of stars. And here is what that means in practical terms. The Orion Arm is not an empty corridor of space. It is alive. It is one of the most active star-forming environments in our region of the galaxy. Massive stars are being born inside it right now, collapsing out of dense molecular cores that have been accumulating material for millions of years. Other massive stars are approaching the ends of their lives, swelling into red supergiants or blue hypergiants that will eventually detonate as supernovae, seeding the Arm with heavy elements and triggering new waves of star formation in the surrounding gas. Some of the most energetic events in our galactic neighborhood: supernova explosions, the formation of neutron stars and stellar mass black holes, the violent winds of young blue giants carving cavities in the interstellar medium. All of this is happening within the Orion Arm continuously, right now, as you listen to this, and our Sun just drifts through it. One quiet, middle-aged yellow star among billions, carrying its small family of planets along for a ride that has already lasted 4.5 billion years. This brings us to the question that sits underneath everything we have discussed so far. If the Orion Arm is this large, this active, this full of stars and gas and violent stellar processes, why does it feel like a footnote? Why does every popular description of our cosmic address jump straight from the solar system to the Milky Way as if nothing important exists in between? Part of the answer is psychological. Humans are not wired to think about structures they are inside of. You do not spend your day thinking about the atmosphere. You do not constantly remind yourself that you are standing on a tectonic plate. You do not feel the rotation of the Earth beneath your feet. These things are too big, too constant, too surrounding to register in ordinary awareness. The Orion Arm is the same kind of invisible. It is not hidden because it is far away. It is hidden because it is everywhere around you. You cannot see its shape because you are part of it. You cannot sense its edges because they are thousands of light years away in every direction. It does not feel like a thing you are inside because your entire frame of reference, every star and cloud and nebula you have ever observed, exists within it. Part of the answer is also historical. For decades, astronomers classified the Orion Arm as a minor spur, a small, unimpressive bridge between the real spiral arms. Galaxy maps showed it as a stubby little feature barely worth naming. The Sagittarius Arm and the Perseus Arm were the important structures. The Orion Arm was just a local wrinkle in the disk. That classification shaped how the public understood it, how textbooks presented it, and how even scientists talked about it in casual descriptions of galactic structure. Minor spur, local spur, Orion spur. The vocabulary itself carried a dismissal built into it, but that classification was based on incomplete data. Astronomers were measuring the arm using only the stars and gas clouds they could see from inside it, which is like trying to measure the full length of a hallway while standing in the middle with the lights off and a flashlight that only reaches 10 feet in front of you. They could see nearby features clearly. They could detect bright, massive stars at moderate distances. But the full extent of the arm remained hidden behind curtains of interstellar dust that block visible light, and behind the fundamental difficulty of measuring accurate distances to objects embedded in the same structure you are trying to map. It took a revolution in measurement technology to reveal what the Orion arm actually is. Radio telescopes that could see through dust, space missions that could track the precise positions and motions of over 1 billion stars, techniques that could measure distances to individual star-forming regions with accuracies that previous generations of astronomers could only dream about. When those measurements finally came in, the Orion arm refused to stay small. The first major surprise arrived in 2013, when a team used very long baseline radio interferometry to measure precise distances to bright maser sources. Masers are natural microwave beacons associated with regions of massive star formation deep inside molecular clouds. These masers are produced when clouds of gas containing trace molecules like water and methanol amplify microwave radiation into intense narrow beams that radio telescopes can detect across thousands of light years. By observing these masers from multiple radio telescopes spread across continents and measuring the tiny shifts in their apparent positions as the Earth orbits the Sun, astronomers can calculate their distances through the same parallax method that surveyors use on Earth, only scaled up to galactic proportions. The measurements revealed that the Orion arm extended much farther than anyone had previously mapped. Stars and gas clouds that had long been assumed to belong to the more distant Perseus arm turned out to be part of the Orion arm instead. The arm was not a short, stubby spur. It stretched far enough and showed enough internal structure that the team concluded it might be a branch of the Perseus arm, or possibly an independent arm segment in its own right. That 2013 paper was the first crack in the old picture, the first serious evidence that our local spiral feature was being dramatically underestimated. In 2016, the same research group published follow-up results that pushed the arm's known length to at least 20,000 light-years. They identified and measured 8 new maser sources within the Orion arm and found that the arm's pitch angle, the tilt of its spiral curve relative to circles centered on the galactic core, and its rate of star formation were both comparable to those of the galaxy's major spiral arms like Sagittarius and Perseus. The Orion arm was not a minor feature. It was, in the words of the researchers, reasonably described as the 5th major structural feature of the Milky Way. Then the Gaia spacecraft entered the picture and changed everything again. Launched by the European Space Agency in 2013, Gaia spent over 11 years scanning the sky and measuring the precise positions, distances, and motions of nearly 2 billion stars before completing its observation phase in January of 2025. Its data releases transformed the study of galactic structure in ways that no single ground-based survey could match. Multiple independent research teams used Gaia data to trace the distribution of young stars, open clusters, and interstellar dust across the Milky Way disk. Their results converged on the same conclusion. A team used Gaia early data to estimate the local arm's length at over 25,000 light-years, consistent with the maser parallax measurements. A separate team used Gaia data to map hundreds of thousands of young blue stars and confirmed the same extended picture. The Orion Arm, once dismissed as a minor spur, was revealing itself as a substantial spiral structure with properties that rival the galaxy's traditionally recognized major arms. Gaia even showed that the Milky Way's spiral arms in general may be less sharply defined than older models assumed, with the boundaries between arms appearing more ragged and complex than the elegant textbook spiral suggested. These discoveries did not just change a number on a chart. They changed what the Orion Arm means. It went from being a minor background feature, something you glance past on a galaxy diagram on the way to more impressive structures, to being a genuine galactic structure, a full-scale spiral arm segment containing billions of stars, active star-forming regions rivaling anything in the Perseus or Sagittarius arms, and an internal architecture complex, enough that scientists are still mapping its details today. And our solar system is buried inside it, not perched neatly on the outside, not hovering near a conveniently labeled dot on a diagram. Embedded within the arm structure, surrounded by its gas and dust and stars in every direction, sitting in 1,000 light-year clearing that barely registers against the arm's full scale. The textbooks that called it a minor spur were not lying. They were measuring a shadow. They were seeing only the nearest, brightest pieces of a structure that extends far beyond what their instruments could reach. The Orion Arm is not minor. It is not a footnote. It is the galactic structure that contains everything humans have ever called home. And its true scale is far more disturbing than even this revised picture suggests. What comes next will make the arm feel less like a neighborhood and more like an ocean with no visible shore. The solar system feels big. It should. It took the Voyager 1 spacecraft, traveling at roughly 17 kilometers per second, over 35 years, just to reach the boundary where the solar wind gives way to interstellar space. The distance from the Sun to Neptune, the outermost major planet, is approximately 4.5 billion kilometers. If you drove that distance at highway speed without stopping, the trip would take over 5,000 years. The solar system, measured out to the theoretical outer edge of the Oort cloud, may extend as far as 2 light-years from the Sun in every direction. That is an enormous volume of space by any standard a human being can personally experience. Now place that volume inside the Orion Arm. The arm is roughly 3,500 light-years wide. The solar system's full extent, out to the most distant hypothetical reaches of the Oort cloud, spans about 4 light-years across. That means you could line up nearly 900 solar systems side by side across just the width of the Orion Arm, not its length, its width, the narrow dimension. And 900 is a generous estimate because most of the solar system's meaningful structure, the region containing all 8 planets, fits within a diameter of roughly 10 light-hours, which is so small relative to the arm's width that it vanishes entirely from any map drawn at galactic scale. Go further. The Orion Arm stretches at least 20,000 light-years from end to end. Some measurements push it closer to 25,000. At that scale, the solar system does not merely shrink. It ceases to be representable. If you drew the Orion Arm as a rectangle on a piece of paper, say 30 centimeters long by 5 centimeters wide, the solar system would not be a dot. It would not be a pixel. It would be smaller than a single atom of ink on the page. You could not mark it, even if you tried. This is the first real confrontation with what it means to live inside this structure. The solar system is not small, in any way a human can intuitively understand. It is simply operating at the wrong scale to register against the arm that contains it. Let me make this worse. The nearest star to our Sun is Proxima Centauri, just over 4 light-years away. That distance is already so extreme that no human technology can cross it in a single lifetime. The fastest spacecraft humanity has ever launched would need roughly 70,000 years to reach it. And yet that distance, the gap between our Sun and the closest neighboring star, amounts to approximately 1/5000th of the arm's length. Imagine standing on one end of a runway 5 kilometers long. The distance to Proxima Centauri, the gap that currently represents the absolute frontier of human ambition in interstellar travel, would be a single step, 1 meter on a 5-kilometer path. That is how the nearest star compares to the length of the Orion Arm. Extend the picture to other well-known nearby stars. Sirius, the brightest star in the sky, sits 8.5 light-years away. On the same 5-kilometer scale, that is roughly 2 steps. Vega, 25 light-years distant, is about 12 steps. Arcturus, one of the most luminous stars in the northern sky, lies 37 light-years away, 18 steps. All of these stars, the brightest and most familiar objects in the human sky, represent distances so trivial relative to the Orion Arm that they barely qualify as motion along the arm's length. And yet, these distances already defeat us. We cannot cross them. We cannot communicate across them in any reasonable time frame. The fastest possible signal, a beam of light, takes 4 years to reach Proxima Centauri, 8.5 years to reach Sirius, 25 to reach Vega. Each of these trips is already beyond the horizon of practical human activity, and each of them covers a distance so tiny relative to the arm that it rounds to nothing. Consider how Voyager 1 fits into this picture. It launched in 1977. It has been flying away from Earth continuously for nearly 5 decades. It is the most distant human-made object in existence. And in all that time, traveling at 17 kilometers per second, it has covered approximately 0.0027 light-years. Compare that to the arm's width of 3,500 light-years. Voyager's entire journey so far amounts to less than 1/1,000,000th of the distance across the narrow dimension of the structure we live in. If the Orion Arm's width were the distance from New York to London, Voyager 1 would not have made it out of the departure terminal. About 4 meters of pavement. That is the fastest object humanity has ever flung into the void, and it has not even begun to matter against the arm's scale. This is where the psychological compression begins. The human mind defaults to treating nearby stars as though they represent the scale of our galactic environment. We say the nearest star is 4 light-years away, and that feels like the edge of our local world. We think of stars within a few dozen light-years as our neighborhood. But our neighborhood is a pinprick. The arm extends thousands of times farther than the distances we think of as vast. The comfortable language of nearby and far away collapses completely when you try to apply it inside a structure this large. Consider what happens when you zoom out just a little more. Our Sun belongs to no star cluster. It drifts through the arm as a field star, unattached to any gravitationally bound group. But other stars in the Orion Arm do belong to clusters. The Pleiades, that small bright cluster visible in winter skies, sits roughly 440 light-years away. The Hyades, an older and closer cluster, lies about 150 light-years from Earth. These clusters contain hundreds of stars each, born together from the same collapsing gas cloud millions of years ago, still moving through space as a coherent group. These clusters are inside the arm. They are specks inside it. The Pleiades, a cluster you can see with your unaided eyes and that humans have used for navigation and storytelling for thousands of years, occupies a volume roughly 43 light-years across. That is about 1% of the arm's width. 1%, the entire cluster, all its stars and gas and gravitational influence, amounts to a tiny clot of material embedded in one small region of the arm's much larger body. And here is where the arm begins revealing just how much it contains. In 2020, a team of astronomers made a discovery that redrew the interior map of the Orion Arm in one stroke. Using three-dimensional dust mapping techniques, powered by precise distance measurements from the Gaia spacecraft, they identified a structure no one had seen before. A gigantic undulating chain of dense gas clouds stretching roughly 9,000 light-years through the arm's interior, connecting many of the most famous star-forming regions in our galactic neighborhood into a single coherent wave-shaped feature. They named it the Radcliffe Wave, after the Harvard Radcliffe Institute where the discovery was made. The Radcliffe Wave threads through the Orion Arm like a spine. It connects the Orion molecular cloud complex to the Taurus clouds, the Perseus clouds, the Cepheus star-forming region, the North American Nebula, and the Cygnus star-forming complexes into one continuous sinusoidal ribbon of gas. The wave oscillates above and below the galactic plane, rising as high as 500 light-years above the disk midplane in some places and dipping below it in others. Its closest point passes within roughly 500 light-years of our Sun. It is, in a very real sense, the backbone of the nearest spiral arm. For years, astronomers had studied these star-forming regions individually. The Orion Nebula was one object. Taurus was another. Perseus was a third. They were treated as separate features, catalogued independently, analyzed in isolation. The Radcliffe Wave revealed that they are all part of a single connected structure, a chain of stellar nurseries strung along the arm like beads on a wire, linked by gas and dust and the underlying gravitational field of the spiral arm itself. And in February of 2024, the story deepened. A team published a paper in Nature showing that the Radcliffe Wave is not just shaped like a wave, it moves like one. Using updated Gaia data to track the three-dimensional motions of young star clusters born within the wave's gas clouds, the researchers demonstrated that the entire 9,000 light-year structure is oscillating. It undulates up and down through the galactic plane over time, driven by the gravitational pull of the Milky Way's disk. The wave ripples through space the way a traveling wave moves through a stadium full of fans, each section rising and falling in sequence as the disturbance propagates along the structure's length. No one knows what caused the wave. No one knows what initially displaced the gas from the galactic midplane to set the oscillation in motion. Some researchers have speculated about a past collision with a massive gas cloud or a dark matter substructure passing through the disk. Whatever the trigger, the result is a dynamic, living feature inside the Orion Arm, a structure that breathes and moves on timescales of millions of years, giving birth to new stars along its entire length as it ripples through the galactic plane. And here is something that makes the Radcliffe wave feel uncomfortably close to home. In early 2025, a study published in the journal Astronomy and Astrophysics showed that the solar system did not merely drift near the Radcliffe wave, it passed directly through it. Sometime during the Middle Miocene epoch, roughly 12 to 15 million years ago, our Sun's orbit through the galaxy carried the entire solar system through the dense gas of the wave's Orion region. The encounter likely lasted several million years, during which the solar system would have been immersed in the denser interstellar environment of a star-forming cloud complex. This was not a gentle brush. The passage would have compressed the heliosphere, the protective bubble of solar wind that surrounds our planetary system, pushing interstellar material closer to the inner solar system than it normally reaches. The researchers suggested that increased dust from this galactic encounter could have penetrated Earth's atmosphere, potentially leaving traces of radioactive isotopes from nearby supernovae and geological sediment layers. The evidence is not yet confirmed, partly because current detectors may not be sensitive enough to pick up the signal, but the implication is striking. The Orion Arm is not just the abstract structure that contains us, it has physically interacted with our planet. Its gas clouds have touched our solar system. Its supernovae may have left chemical fingerprints in Earth's rocks. The arm is not a backdrop. It is an environment that has reached down and altered the conditions on the surface of our world. 9,000 light years. A single connected structure of gas and newborn stars oscillating through the interior of our spiral arm. And we only discovered it existed in 2020 because we finally had the technology to see it. And we only discovered that we had passed through it in 2025. This is what the Orion Arm contains. Not just scattered stars and isolated nebulae, but enormous coherent structures spanning thousands of light years, hiding in plain sight because we lacked the three-dimensional mapping tools to recognize them. The arm is not a simple corridor of stars. It is a layered, dynamic environment with internal architecture that scientists are still uncovering. The Radcliffe wave is the most dramatic recent example, but it is not the only large-scale feature inside the arm. The arm contains vast complexes of molecular gas, regions where hydrogen exists not as individual atoms, but as molecules packed into cold, dense clouds with temperatures just a few degrees above absolute zero. These molecular clouds are the raw material for star formation. They fill the arm's interior in enormous concentrations, some of them spanning hundreds of light years across and containing enough mass to form thousands of stars. The Orion Molecular Cloud Complex, the parent structure of the Orion Nebula, stretches roughly 240 light years from end to end and contains roughly 200,000 times the mass of our Sun in gas and dust. Stars are forming throughout this complex right now, collapsing out of dense cores buried inside the cloud's darkest, coldest regions. The Orion Nebula itself is just the most visible piece of a much larger system. The Cygnus X complex, which lies near one end of the Orion Arm in the direction of the constellation Cygnus, is even more massive. It contains millions of solar masses of molecular gas spread across a region several hundred light years wide. It is one of the most prolific star-forming regions in the entire galaxy. Some of the most massive stars known, blue supergiants that burn through their fuel in just a few million years, were born inside Cygnus X. Their intense ultraviolet radiation ionizes the surrounding hydrogen, causing the entire region to glow with a soft, diffuse light that radio telescopes can trace across thousands of light years. These are the stars that define the arm's boundaries, the luminous beacons that make spiral structure visible from across the galaxy. And they live and die inside the same arm that holds our sun. We have now reached the end of our journey through the Orion Arm. We began with a simple question about where we live in the universe, and we discovered that the answer is far stranger and far grander than the familiar three-step address we usually recite. Between the solar system and the Milky Way, there is a spiral arm 20,000 light-years long and 3,500 light-years wide. It contains billions of stars, some of the most active star-forming regions in the galaxy, an oscillating 9,000 light-year wave of gas and newborn stars, and 1,000 light-year cavity carved by ancient supernovae that we call home. Our sun drifts near the inner rim of this arm, orbiting the galactic center once every 250 million years, passing through dense clouds and open spaces, through periods of intense cosmic radiation and long stretches of calm. The arm is not our eternal home. It is our current address, a temporary resting place on a journey that will continue long after our star has faded. And yet, in the quiet of this moment, as you sit in your chair, listening to these words, the Orion Arm surrounds you. Every breath you take contains atoms that were forged inside its stars. Every photon of starlight that reaches your eyes has traveled through its tenuous gas and dust. You are not an observer looking in from outside. You are part of this structure, embedded in its substance, carried along by its motion. The arm is not something far away that you need to imagine. It is the space you occupy. It is the medium of your existence. Perhaps that is the most humbling realization of all. The scale of the Orion Arm is not a distant abstraction. It is the immediate reality of where you are. It is the frame within which all human history has unfolded, and within which all future human stories will be told. The stars you see at night are not scattered randomly. They trace the shape of a vast spiral feature that extends far beyond what any telescope can resolve from the inside. And you, and everyone you know, and everything humanity has ever achieved, are a fleeting, beautiful part of that cosmic structure. The Orion Arm is home. And home, it turns out, is far larger than we ever dreamed.